Today I'd like to look at a problem where we are lifting something up to a higher height. And by doing that, we're adding gravitational potential energy. So we're doing a work calculation now by adding gravitational potential energy. So for example, say that we have this container full of water and we have a pipe running up to ground level. So imagine this container is underground and we're going to pump all that water up to the ground level. So there's a raising of the water. The water existed in this tank to start with, and then at the end it's all laid out on the ground. So what we're interested in is how much energy did we add to the water? It's got more gravitational potential. The problem is all the water got lifted different amounts. You know, if we just took that whole container of water and just dug it up and set it on ground level, there'd be no need for calculus because this has some weight and it would have been lifted 4 feet, or I guess plus the 2 feet, so 6 feet. But that's not what's happening. If we pump this all out to the ground, some water that was here at the top of the tank, its displacement up to here is just a little bit more than 4 feet. Right? Water near the bottom of the tank is getting displaced almost 6 feet. And every little speck of water in between is getting displaced a different amount. So that's where the calculus comes in. We need to account for the fact that every little layer of water, if you like, is being lifted up a different distance. And so that's why our idea of slicing like we do will allow us to do this. So first of all, let's put a coordinate system on this, and we're free to set up that coordinate system however we like. I like to make the bottom 0. So this is going to be my y-axis measured in feet, just like the dimensions of my box. And so 0 here at the bottom. The box is 2 feet tall, so there's 2, and then another 4 feet to the surface, so that would be 6. Okay. So I need to solve the issue of all of this water starting at different heights, but it all ends up at 6, right? So that's what's going to get partitioned. Think of us slicing up that water. So we're partitioning this interval from 0 to 2. And let's try and figure out the work on just one of those partitions, one of those subintervals, I should say. So y sub k minus 1 up to y sub k. Now I'm going to draw that over here on our tank. So conceptually, the idea is we're taking a chunk of that water. And so this slice of water here that has a height of delta y sub k. How much work would be done in getting that water up to ground level? Well, we still have the same problem, right? Even in this little slice, that little speck of water at the bottom of our slice is traveling a little bit farther than a speck of water towards the top of that slice, and every little level in between. So that's where the approximation comes in. We're going to assume all of this water is at one height, even though it really isn't because it's got some thickness. So that's where our representative point comes in. So we pick some arbitrary c sub k in that subinterval, and we're going to pretend that all that water is at c sub k. So let's think about what we need to compute here. Work, remember, computationally is force times distance, or displacement. So our W sub k here, force times displacement. The force, in this case, is gravitational force, right? We're adding gravitational potential, and it's really just the weight times the distance. We saw this at the beginning when I was talking about energy. So I need to know how much does this little slice of water weigh, and how far is it being displaced there? Well, that's where this information comes in. I need to know something about water. Typically, we would use something like 62.4 pounds per cubic foot. That's the weight density. So this little w, which is unfortunate, the book likes to use little w for weight density. We've got big W for work. So those are two different things. I'll try and emphasize that that's a little w there. But a cubic, so if you had a box that was 1 foot by 1 foot by 1 foot full of water, it would weigh 62.4 pounds. So that's our weight density for water. So I need to know how much does this chunk of water here weigh. So it has some volume. If I take that times the weight density, remember weight density is weight per volume times volume will give us weight. So that volume times weight density is just giving me the weight of that slice there. Now, how far it's being displaced. Okay. Now let's fill in the details there. This would be approximately, and the reason it's approximate comes into this displacement part, because we're going to assume all that water is at C sub k, which it's not. So what is the volume of our slice? This little chunk of water is a rectangular solid, just like the bigger tank, and it's 5 foot by 3 foot, but this dimension is only delta y sub k there. So volume is 5 by 3 by delta y sub k. Weight density was given. That'll always be given to us in a problem, 62.4. And I don't expect you to remember physical constants, so you don't have to memorize that that's 62.4. That'll always be provided for us. Whatever the liquid is, it could change if this was crude oil or something else. And then how far is it being displaced? Well, it's starting, we're assuming all the water starts at this C sub k and is being lifted up to 6. So bigger minus smaller, that distance is 6 minus C sub k there. So our displacement (6 minus C sub k). So what have we done? We've assumed that all this just moved kind of as a solid, right? If you imagine that that water was frozen as ice and we cut that chunk of ice and just set it up on ground level, that would be exactly the work, because all the water would move that same amount. But it doesn't, so that's why it's approximate. This displacement amount, we're taking a single point in there and assuming it all existed at C sub k. But again, as those shrink down, as that delta y sub k gets smaller and smaller and smaller, that little bit of difference in that subinterval will start to decrease and our approximation becomes exact. Okay, so let's set up our integral. So it's going to become exact when we let the norm of our partition go to 0 of the sum of all those little bits of work. And that's the expression there. I'll neaten this up a little bit, at least multiply the 5 and the 3. So I've got 15 times 62.4, just kind of gathering up the constants. The 6 minus C sub k and the delta y sub k. And that, by definition, is the definite integral. Now, let's think about our limits here. And remember, if you always draw that partition, what is being sliced? In all of the applications we do of integration, there is some interval of interest, and that interval is being sliced. as soon as you draw that, you know your limits because that's the interval that's being sliced, 0 to 2. One of the questions I often get is, well, how do I know that I'm not integrating up to 6, right? I'm lifting all that stuff up to 6, so maybe I should integrate up to 6. Just ask yourself what got partitioned, what got sliced up. There's nothing being sliced up here, right? It's just the water that's getting sliced, so that's our partition from 0 to 2. That's your limits of integration. There should be no question once you have the partition drawn. And then we've got 15, 62.4. The variable is y, dy. So that would be our integral. This would tell us now exactly what the work is when all of this water ended up at one height there of 6, just pumped and laid out on the ground level. This would be, just take the constant out of there and you're really just integrating a fairly simple polynomial at that part. What about our units? We'll just leave the details of the integration off here. What would the units be? So remember, what are we calculating? Work. And when you're thinking of units, think about this. Work is force times displacement. Force units, well, force is gravity, right? And the force units were really keyed in right here. That was the only place we see the force units is in that weight density. So we know force was measured in pounds. And all of our distances were measured in feet. So the units here, foot-pounds. So if you remember work as a force and a displacement, it's a force unit and a distance unit. Just look at your problem and you can see which one of the force and which one of the distance. Typically, we're going to not focus too much on having to convert between units. So if this one's given in pounds per cubic foot, these measurements will be in feet. We don't want to get sidetracked by a lot of unit conversion stuff. We just want to focus on the calculus there. One last note. People will sometimes get bogged down in thinking about the mechanics of how this water is being pumped. Right? How is this pump set up? Is there a float that floats on top and kind of skims it off the top? Is it a fixed pipe that goes down to the bottom? Because people think this makes a difference, right? If the water starts up here but has to flow down and then back up and then it goes to this highest height, does that matter that this pipe goes above 6 feet and then it drops back down? Don't worry about any of those details. Yes, there's a lot of stuff going on there, but in the end, work is simply change in energy. So all you need is a snapshot of the beginning, water in the tank. That's your initial situation. Snapshot at the end, all the water's on the ground. That water is now at a new height, so it has more gravitational potential, and that's how we would figure it out. It doesn't matter if we pump this up the pipe, put it in a truck, drive it around town for a while, bring it back, dump it on the ground. None of that in between matters. The new condition is that it's all on the ground. The old condition was it was in the tank. The details of how it got there don't matter. We're just interested in how much work was done on the water. Those details, you know, the construction of the pump and how that water gets there would be important if we were interested in the amount of work done by the pump. For example, the pump would have to lift it all the way to the top, but gravity takes over from there and lowers it down. So that would be a different kind of question. So we're not interested in how much work the pump does. We're just interested in how much work was done on the water. And so any of those details we can just forget about and just focus on the initial picture and the final picture.